So this is a video I've been a bit nervous to publish, but it's about time. That's because this topic deals with my own work and my own ideas. We all remember those arguments we had as kids about who got to go first on the video games.
I call first. Oh yeah? Well, I call first times infinity. Oh yeah? Well, I call it first times infinity plus 1. No, because infinity plus 1 is still just infinity. Oh yeah? Well, fine. I call first times uncountable infinity.
The concept of infinity is one of the most popular topics in math communication today. Among the properties of infinity, one of the most popular is the idea that it comes in different sizes, countable and uncountable infinity. This comes from a branch of mathematics called set theory. These terms are supposed to distinguish between different sizes of infinitely large sets, with countable infinity being defined as having a one-to-one correspondence with the natural numbers, or the counting numbers. The notation used to identify this size of infinity is called aleph null. Some examples of sets that fall into this category could be the set of all even integers, or the set of all odd integers, or the set of all integers that contain only 9s, or the set of all powers of 2. What all these countably infinite sets have in common is the members are sequenced in an order that has a beginning. The natural numbers all uniquely identify a member of the set, and every single member of the set belongs to a unique natural number identifier. If any one of these properties is missing from the infinite set, then the set is uncountably infinite. This is where most math communicators point out that the set of all real numbers between 0 and 1 is uncountably infinite, and therefore a larger set of infinity than all the natural numbers. Two communicators of note are Michael from Vsauce and Dr. James Grimes from Numberphile. Both highlight the lack of a smallest number from which the infinite set would begin. It's this exact concept which causes James Grimes to suggest that it would be better to name these infinities listable and unlistable infinity.
Countable, and I don't like the name countable. And Brady gave me a little bit of a just there, because if you're talking about infinity, you can't count infinity, can you? Because it goes on forever. I think it's a terrible name. I prefer to call it listable. Can we list these numbers? All right.
Both also mention Cantor's diagonal argument as a proof that the set of all real numbers between 0 and 1 are uncountably infinite. Cantor's diagonal argument states that if you have an infinite set in which all the members have infinitely many digits in their decimal expansion, a new number can always be created with a piecemeal operation by taking the first digit from the first number, the second digit from the second number, the third digit from the third number, and so on to the nth digit, and altering them by 1 such that the new number differs from all the other numbers in the set in at least 1 decimal place. Personally, I think there's a better way to do this and a better way to define these terms. First, I'm going to start by building the countably infinite set of all real numbers between 0 and 1. According to Veritasium, Cantor struggled to put the reals between 0 and 1 into a well-ordered set. This method accomplishes this. It would also seem that when taking this mapping function to its limit, we've created a one-to-one correspondence between the natural numbers and all the reals that lie between 0 and 1. The reason that mathematicians say this isn't true is based on definitions and axioms. It starts with the axiom of infinity, which defines the first infinite set as the natural numbers. Part of what defines the countably infinite set of all positive integers is the fact that this set does not include any numbers which have infinitely many digits in its decimal expansion. This means that the infinitely many processes or operations that make up the function for building a countably infinite set is not a supertask and therefore doesn't complete. A supertask is an infinite sequence of tasks that occur within a finite interval of time. Even though this is an argument over the logical foundations of mathematics rather than a rigorous proof, this is where a provable contradiction exists under the current foundations of mathematics. That's because the proof that 0.9 recurring equals 1 depends on an infinite sequence of mathematical operations being able to complete. This comes in the form of infinite geometric series. If we are to accept this as proof, then we should be able to accept my function for building the set of all real numbers between 0 and 1 as countably infinite. The other problem I see are assumptions made in regards to Cantor's diagonal argument. The first assumption is that Cantor's diagonal argument utilizes an infinite process of the same order of infinity. Also, for the set of all reals between 0 and 1, there is a logarithmic relationship between index and decimal expansion, whereas Cantor's diagonal process for building the new number utilizes a linear relationship between index and decimal expansion growth, meaning they are asymptotically incompatible. I think I have a better way with no contradictions, and it would render the continuum hypothesis a false dichotomy. Hey, so welcome to another edition of Future Mike here. I just wanted to make it perfectly clear what the difference between a countable and uncountable infinity is. A countably infinite set is defined as a set in which all the members can be reached within a finite amount of time. So if you do what I did for the reals between 0 and 1 or the natural numbers, you will never reach a number that has infinitely many digits in its decimal expansion. So if you name one of those digits, you won't be able to reach it within a finite amount of time. So that's why it's not countably infinite. That's how it's defined. But I present to you Cantor's argument for how he orders the rationals into a countably infinite set. And just because he chooses to do it by symbolizing the numbers by fraction instead of by decimal expansion, you have numbers like 1/3, which will have an infinite decimal expansion that pop up in the middle of the set. So how you choose to symbolize the number you're representing actually has an impact on how you define the set, which is why I think the paradoxes arises. I just wanted to make that perfectly clear. Instead of basing the classification of infinities on size, infinities should be classified based on the properties that are preserved. And when it comes to countably infinite or uncountably infinite, the property that seems to be under the gun is commutativity. So, if you'd like commutativity to be preserved, simply allow the function to complete. If commutativity is not a goal, and the goal is to see how the function evolves, then simply have the function approach infinity rather than having the function complete. When it comes to classifying sets, there would no longer be such thing as uncountably infinite in the way we are currently familiar. That's because, although I reference building sets, sets are said to exist by axiomatic definition and are not considered tasks which need to be completed. And the defining characteristics that separate infinities into classifications are predicated upon operation. One of the consequences of restructuring the foundations of mathematics, like I have stated here, is the resolution of some long-standing paradoxes in mathematics. For example, the Ross-Littlewood paradox. The resolution of this paradox solely depends on whether or not you choose to preserve commutativity or not. The Ross-Littlewood paradox is a thought experiment in which you have balls labeled 1 through infinity and a box. On the first step, you put balls 1 through 10 in and take out ball 1. Your second step, you put balls 11 through 20 in and take out ball 2. Third step, you put balls 21 through 30 in and take out ball 3, and so on and so forth. The question is, how many balls are in the box at the end of the supertask? The answer is 0 if the symmetry of commutativity is preserved. The answer diverges to infinity if the order matters. Either answer is true. What matters is context and which one is useful. Because at the end of the day, math, although might be the greatest tool at our disposal, is still just a tool.